2.6 Traceability in a spice. As in the foundation core syllabus, a spice additionally requires bidirectional traceability. This allows the tester to analyze impact, trans-impact analysis, evaluate coverage, track status. Moreover, and this allows the tester to ensure the consistency between the linked elements textually and semantically. A spice differentiates between vertical and horizontal traceability. Vertically, a spice requires that stakeholder requirements be linked across all levels to the software units. In doing so, the link over all levels of development ensures consistency between the related work products. Horizontally, a spice requires traceability and consistency between the work results of the development and the corresponding test specification and test results. In addition, the best practice requires bidirectional traceability between the trend requests and work products affected by the trend request, because trend requests are often initiated by a device. Bidirectional traceability establishes between trend requests and the corresponding defect reports. Because of the associational larger number of links, a consistent trend of tools can be helpful. This allows the tester to efficiently create and manage the dependencies. 2.2 ISO 26262 Functional safety and safety culture. Objective of functional safety for EE system. The functional and technical complexity of embedded system is constantly rising. At the same time, powerful software based electrical and electronic systems allow new complex functionalities, such as the automation of the driving function in the car. Due to the increasing complexity, the risk of an erroneous action happening during development is increasing as well. The consequence can be an unrecognized defect in the system. For systems with an inherent risk potential for life and limb, the responsible safety engineer or safety management therefore needs to analyze potential risks. If there is an actual risk, suitable measures need to be identified to mitigate the possible risk impact to an acceptable risk level. The methods for the execution of such analysis are summarized in the standards for functional safety. The foundation standards IEC 6192A, the International Organization for Standardization, ISO, adapted ISO 26262 from the standards, which is available in its second edition from 2018. Functional safety involves ensuring that EE systems operate without causing unreasonable risk due to hazards from malfunctioning behavior. In this sense, the term is to be differentiated from all the related terms such as information security or cybersecurity, product safety, or occupational safety. Occupational safety and cybersecurity are not in focus of ISO 26262. However, a lack of cybersecurity can endanger functionality, can endanger functional safety. Both functional safety and cybersecurity contribute to product safety. Contribution of the tester to the safety culture. Within a product development according to ISO 26262, monitoring only your own organization's processes is not sufficient. All participants need to follow a cross-process approach. Everybody must understand their impact on the development process and the safety of the final product. This includes external partners and suppliers. The participants must understand that their own actions do not happen independently of other processes. Each step of development constitutes an essential contribution to both compliance with and implement of the implementation of the safety relevant requirements. This responsibility does not end with the market launch. It continues until the end of the safety life cycle. The tester contributes to the safety culture by participating responsibly in the software development lifecycle phase and by carrying out their work with a continued view of the overall context of the product development. Integration of the tester in the safety lifecycle. The safety lifecycle describes safety-oriented activities during product development. It starts with the first product idea and the identification of possible risks. After the specification of resulting safety requirements, the implementation into a specific product follows. The safety life cycle ends with the disposal of the product at the end of its life. The safety life cycle according to ISO 262 goes through the following phases. First phase, concept phase. Second phase, product development. This phase ends with the release for production. Third phase, production, operation, service, and decommissioning. The tester works primarily in the first two phases. Transfer to the product within the third phase led to a return to the first or second phase, depending on their extent. Therefore, the tester also participates in modifications based on the safety-related requirements. Task techniques are selected, and test cases are designed for the verification and validation of these requirements. The tester will then perform those tasks in the respective phases of the product development. Task planning normally takes place within the concept phase. Adjustments to the resulting documents in the task plan or the task specifications, however, be necessary in any phase. Task execution takes place primarily at transition between the individual phases of product development. For example, transitioning from implementation to software integration, and then the hardware-software integration. Moreover, the tester significantly contribute to the transition to the third phase with their test activities. Structure of testing of specific parts of the standards. Design and structure of the standard. The ISO 26262 consists of 12 parts. Vocabulary. Part 1. Management of functional safety. Part 2. The phases of the safety life cycle. Concept phase. Part 3. Product development at the system, hardware and software level. Parts 4, 5, 6. Production, operation, service, and decommissioning. Part 7. Supporting processes. Part 8. Issue-oriented and safety-oriented analysis. Part 9. Guidelines on ISO 26262. Part 10. Guidelines on application of ISO 26262 to semiconductor. Part 11. Adaptation of ISO 26262 for motorcycles. Part 12. A pass from Part 1, Part 10. A pass from Part 1, Part 10, and Part 11. Its pass contains a general introduction, the scope of application, normative reference, requirements for compliance with the standard. These are followed by the specific topics of the corresponding parts. The structure of their description is the same in each part. The activities that are to be carried out are described via the recurring structure in all parts. Objective, zero information, introductory information, prerequisites, prerequisites, further supporting information, requirements and recommendations, work results, relevant parts of ISO 26262 for the tester. For the software tester, the software verification and at least partly the system validation are paramount. Apart from Part 1, vocabulary, several other parts are also of special interest. Parts 4 and 6 provide detailed information and requirements regarding recommended software verification measures. This applies to the selection, design, implementation, and execution of the corresponding verification measures. In doing so, these parts focus on the test and verification specific aspects of the system level, including safety validation, and the software level. If hardware-specific aspects are also relevant for this work, the tester will find those in Part 5. Aspects concerning both hardware and software are considered within the scope of the hardware-software interface. Parts 4 and 6. Part A has a special role as it describes for process-specific characteristics of the verification at all test levels. In addition, it contains requirements for supporting processes that are critical for ensuring standardized processes, such as configuration management and the qualification of tools. In parallel, the tester will find adapted methods tables based on the newly introduced motorcycle safety integration level (MSIL) assessment for motorcycle projects. The influence of criticality on the extent of the test. The criticality levels of issue. The issue is a measure for the reward reduction through measures of functional safety. Such measures can be, for example, an independent safety function for monitoring an EE system, or the implementation of specifically defined methods. For higher risk level, more elaborate measures can be necessary. At the beginning of the process, a term of experts performs a hazard analysis and risk assessment for the product. For each hazard identified by this analysis, the term determines an issue using the methodologies defined in the standard. In the next step, the team defines safety goals and safety requirements. These have the same issue as the underlying hazards. ISO 26222 defines four levels from RCA low for low up to RCD for high safety requirements. If the results of the hazard analysis and risk assessment lead to requirements below RCD, below RCA, then in terms of the standards, those are not safety relevant. For such requirements, there are not any functional safety relevant related action needed, and it's enough to cover such requirements using already existing quality management system (QMS). For particle reason, those requirements are often marked QM (quality management) to distinguish them from issue-related ones. Influence an issue on test techniques, test styles, and the resulting of test scope. The determined issue directly influences the extent of the test to be carried out by the tester. Depending on the level of issue, the ISO 26262 standard recommends the execution of different measures or package of measures. In doing so, the standard recommends more extensive and detailed measures for higher issue. For lower issue levels, the execution of the specified measures are often optional. ISO 26262 specifies these levels of recommendation: no recommendation, recommended, and highly recommended. The general understanding of these recommendation levels is that where a method is listed as highly recommended, it must be applied, while a method listed as recommended should be applied or unreasonable for not using it shall be given. In the case of no recommendation, the standards do not provide any recommendation for or against the use of the measure in question. It can be used as a supportive measure without any concern. However, its execution does not replace the measures recommended or highly recommended by ISO 26262. For the tester, this means that the standard recommends specific test techniques and test times for the safety relevant system depending on the issue. Tester can only decide freely to the extent that the standard allows for the special case. For example, the use of equivalence partitioning and boundary value analysis are merely recommended for RCA. In the other hand, for the RCB or higher, those techniques are highly recommended. The issue is not a characteristic of the entry product. It is tied to a specific safety goal and safety requirement derived from it. For the sample safety requirements with different issues can therefore result in significantly different test efforts. This must be taken into consideration by the tester when planning the test scope.